All right, we're back. Oh, that took some doing. Well, anytime we end up doing it this way, it takes a little while to. So I wanted to do just one tech experiment with EMG and nerve conduction studies. It's basically set up more or less. I do have to pull out some of the electrodes and things. I wanted to talk a little bit about rest, particularly focus on a little bit of basically the hearing mechanism, a little bit about taste, a little very small amount about taste and smell. That's part of it. Sort of generically looking at that. And I don't think there's a whole lot else physiologically to be concerned about after that. These are some of my new thingies. You got a discount, those little leads. So I'm just pulling out the ones we're going to need. The red, black, and green once again. Voicing through the ones we need for this experiment. And we will begin. I looked at some other stuff that looks interesting that we'll have to try. So let me just, because I want to catch up with this. Once we finish this, lecture-wise, we'll finish the neurotransmitter thing, I'm sure, Wednesday. And that means Friday, we'll probably jump to autonomic nervous system, which is chapter 14, which is important, and then follow that with endocrine. Those are the next lab topics. Once we finish with this, now we'll hit heart. So heart electrocardiography, and that's another tech-related lab that we'll be doing as well. That's what's going on. We're all good? Excellent. Outstanding. So I loaded a couple of PowerPoints that were there. I think I had C and D. I wonder if I have B up here. There's B and C. We'll do those. So we're done with that. So we kind of ended, if you recall last time, and I checked because it's been a while because we did the wet lab the other time too. All the visual stuff that was coming near the end, I'm just scrolling through, and it brings us to this. And these are relatively short. The hearing is a little bit longer. And then there is not a whole lot left in the rest of, I think, in the rest of this particular chapter. Because we looked in anatomy, we looked at the peripheral nerves and what they went to, radial nerve and musculocutaneous and sciatic nerves. So we did that. We did the plexes. We did the cranial nerves, right? So I can't see rebuilding the wheel with that necessarily. And so the last PowerPoint in this particular chapter deals a lot with some of the, some sort of generic things about nerves that I don't think are terribly relevant and we have so much content to deal with. And yes, I sent you an email about choosing a topic. It's time to choose a topic within the next. Let's try to have it done give me a topic within about 2 weeks, end of the month. Okay, fair enough. Like I said, I don't care if you recycle. You're doing an honors presentation, recycle it. As long as it's got physiology in it. If you did a paper for third grade and it has physiology in it, we can do that. Yeah. How much force do I have to generate to smack somebody with a lacrosse pole? We'll find out. That kind of thing, or a hockey stick. I give up. All right. So, I don't look, and if you're doing a presentation for Science Day, some people, fine, rehearse, because they'll give you an opportunity to present it, and then we'll figure out the logistics of the presentation. I think it's fun. You would like to think that folks of your at an advanced stage in a scientific program are going to have to learn to do presentations. To me, that's my happy place. I like being the center of attention when I'm here. I like being anonymous when I'm here. Okay, moving on. So, olfactory. You might remember the anatomy. You had the olfactory nerve, cribriform foramina, tiny nerve endings. These are chemicals. The whole idea with taste and smell, which are very, very similar, is dissolution. So you have to dissolve, whether it's an odorant or something with taste, in saliva or mucus. That's part of their purpose. So they have to be dissolved aqueously. to be picked up by these chemoreceptors. And so it's the same thing. It's nothing different about that. This was the anatomy of it. Again, you see the presence of the bipolar neurons. So the olfactory elements. So effectively, it's olfactory. It's a chemical signal to an electrical signal. But now the bipolar are just creating that electrical signal. I think modifying it or adapting it so we can interpret. And smells are usually a combination of many factors that are there. And then the anatomy we've seen before. So the olfactory nerves, bipolar, terminate. You have olfactory cilia radiating from it. It dissolves. It gathers up the chemicals. The good news here is it comes back. We saw it in COVID when people lost sense of smell and sense of taste, where it started to come back, which is a good thing. And the same thing here. Even if you're near a fire and it's like the inside of your nose gets singed, it's rarely permanent in nature. That's there. If you look this up recently, since the time of this publication, you can see 2020 down here. It means, I think, that there's a whole lot of change. Our sense of smell may not be as great as an animal sense of smell, which is anatomical. My dog has a poodle nose. He's all nose. It's a big nose. So it's today they're thinking thousands to hundreds of thousands of smells, a lot more than we really think. Maybe not. We may not have quite as selective as certain other species because we use it differently. So we have a lot of different receptors with unique proteins, as you can see here. It's very straightforward. Pain and temperature, obviously. And again, the beauty of this, if you remember Cranial Nerves 101, is smelling salts. Something like that that's very distinctive, we really pick up on right away. So much so that it goes into our cerebral area and wakes us up. That's the idea. So smelling salts have that ability to, get somebody out of a state where they fainted or they're not nearly as with it as maybe you want them to be, particularly to talk to them or examine them. So it does have to be in a gaseous state and dissolve. So much that is there. Binding into typical G protein passageway. Sodium and calcium channels are the ones that are involved in this particular passageway. I don't think that's a big deal as much like we did in lecture today with the sodium and potassium. That's a big deal. Less so here. So depolarization, influx, and then of course we have olfactory adaptation. We've all seen this up in the lab there when it stinks, or any other lab, like the micro lab. You go, oh, brother. And then, after a while, you don't notice it as much. Typical G protein passageway, not a whole lot to talk about there, or the anatomy. So there's a variety of things so if you're really into the special senses and smell, this is where the ear, nose, and throat, folks, they look at the intricacies here. And I've always found that to be true. In whatever field you're in, if you're in that field, then you'll really look at the intricacies that are about that. If you go into physical therapy or training, then you really begin to look at in depth into muscle physiology, for instance, that are there. So it can go directly to the frontal lobe. That's the idea of the smelling salts. Others require a little bit more processing, and that's where we get that emotional response that's so unique. Where odors, we use smell a lot to try to trigger memories in amnesiac patients or people, which they'll trigger older memories and things like that, or ones they have sort of sequestered. And it's just like, for me, bakery. Just saying. Or, like I told you, my kids threw up, I was terrible, Dad. You're on your own. Your parents do that to you? Here's a plastic bag. Go. Tell me when you're done. What?
My 21st, my dad just left me in the driveway.
Okay, fair enough. As long as he didn't run over you, I guess it's okay.
Yeah, he's good. He just went to bed.
She's back. She's fine. Stay out there. And again, usually head injuries play a role. We do see the hallucinatory aspect interesting, I think, because a lot of times that's the aura. You get visual and olfactory, different, it's that little warning sign sort of built in to get yourself protected if you're going to have a seizure or, basically. And like taste, extraordinarily similar, a great abundance of taste buds. Yeah, we didn't do the anatomy then. We're not going to do it now. And it's not just in the tongue, they're through the palate, on the sides of the cheeks, pharyngeal, even epiglottis. I told you, and that's where in cooking science, you have certain things that target that when you're trying to blend certain tastes. Because that's what you want to do with it's not just salt, sweet, sour, bitter. It's umami, it's heat, it's that unctuous sort of fatty mouthfeel flavor. All that type of stuff that you do that are part of it. We looked at that before. Technically, they call them gustatory hairs. Really, there's just the anatomy of looks almost like microvilli with little openings in the membrane with protein receptors that effectively are with the insert. And you'll see it illustratively if you forgot it. That are there. These little flash-shaped epithelial cells, okay, and the gustatory hairs into these taste pores are covered in saliva, and different types of ones that are involved, whether it's serotonin. And this is one thing we talk about neurotransmitters, where ATP is actually a neurotransmitter. So there's just some interesting nuances. Not a big deal for us. And you can see, and that's when you burn your tongue or injure it or something. It's easy even after certain types of infection. Throat, strep throat. Your taste sense kind of goes. So the buds it's really lower when you get down into this neck of the woods in these little naturally occurring clefts. And here's this gustatory hair, and effectively it's like these little passageways in between with surface area, which will react to different things. Again, the major tastes that they're consistently aware of. And that's all part of this stuff. Like I said, with cooking science or chef school, you're trying to hit all those. So when somebody takes a bite, it's like, whoa, that's really good. And you try to hit as much of that stuff as possible if you can. And then the other stuff, heat receptors, this affection certain folks have genetically for fatty things that are there. I mean, there's all sorts of this. And again, many of them are even protective in nature, as you can see here. Not a whole lot. Dissolved, diffuse, contact one of those gustatory structures. We call them tastants. The neurotransmitter then basically starts the whole thing. And notice they adapt relatively quickly. So something like that, might overwhelm you at first, unless there's so much. We can usually tell it's you put too much salt in that, or that kind of a thing. It's interesting that bitter, because it's the one that really warns you, are the most sensitive. Like I am terrible at swallowing pills, and inevitably I've got pills that dissolve. The minute you put them, it's like, oh my god, yeah. Mash it up, applesauce, happy days. A little kid. How many 72-and-a-half-year-old men go into the pharmacy? Can I get it in a liquid? There aren't a lot of us who do that. Oh, I love this. Gus Dewson. Not Gus Triondos, but who is? Catcher for the Orioles back in the 60s. Early 60s. Not Andy Etchebarren. My wife and her mom on Sportsnet Plus, they were replaying like aspects of the 79 that the Pirates were in and won a World Series. That was in 79. when they played, because in both those World Series 71, 79, they played the Orioles. Great teams. Those Oriole teams were good. So and there's not a whole lot to know. Remember the nerve structure down the road. You probably need to know this. These are the kinds of things I see on board exams. I see these on GRE type exams, depending on the area you're looking at. Remember, facial nerve, think tongue being part of your face, glossopharyngeal, the posterior third of the tongue being more of your throat, vagus nerve, even the back of the throat. We start to look at with the epiglottis. And basically, that's, again, usual thing, head and neck injuries, etc. Voila. So that's done. So we'll X out of this, and now we get in. I had already started to look at this. This was the hearing part of the program. So we looked at the anatomy of this earlier when we were in last term. For those who were here for the anatomies, most of you were. Fairly straightforward. And effectively, what's the ear other than an amplification chamber that's going to take sound, mechanical energy at particular wavelengths, and amplify it and direct it by caught in the external ear, taken by the hammer, anvil, and stirrups, malleus, incus, and stapes, and into what's called the oval window, that where the stapes sit, creating whatever degree of taking that mechanical energy and transiting it in. Now we have to somehow convert this magically to an electrical signal based on the particular wavelength it is, and then how frequently we repeat that wavelength. So it's a matter of frequency, the nature of the sound, and how frequently that is signaled to us. But again, loud or soft, whatever, if you want to think of it that way. Again, in this case, frequency, not 450 versus 451 nanometers, is its frequency of how many. So and we have quite an extensive range, and even things that are inaudible will technically have us. So look again at the anatomy, fairly straightforward. Again, the receptacle, the auricle, even though it's not essential, okay? And obviously the entry point covered by the tympanic membrane, which is nothing more than a drum head for that sound. And yes, it's kept lubricated by sebaceous glands and modified glands that are probably apocrine glands for earwax, caruminous glands. Some people have troubles with that. And they'll just basically collect it, and the eardrum sits on the external auditory or acoustic meatus in the temporal bone. And it vibrates. And that vibration, because it's adherent to the hammer, the anvil, and stirrups, malleus, incus, and stapes, transmitted to the oval window there, as you can see. And then depending on the transmission and movement of your head, it will either go into the semicircular canals for motion of head positioning, or into the cochlea. And I mean, these are extraordinary tiny. Remember the anatomy, split pea size. They're very tiny. So the middle ear, mucus in there, obviously problems when it accumulates. My ears are stuffy now, as they typically get toward the latter part of the longer day that I have Monday. In by the oval window, out by the round window. There's a little indentation. There's, again, the mastoid behind it to a certain extent. I think that that enhances the amplification that's there. The eustachian tube, really a chamber to more or less equalize pressure that you can have. Some people are very good at it. I'm terrible at getting that clear. I get terrible ear problems when I fly. I chew nonstop. Cow. There's not enough gum in the world. I have no idea how my wife sleeps on a plane. Okay, a couple little muscles. Remember those tensor tympanics. Adjust attention. They're there to deal with adaptation to sounds. How we can, for a period of time, get used to louder sounds and things like that. And again, we talked about it before, how persistent exposure to loud sounds for long periods of time without some type of protection are really significant. And you see, in some places, it's mandatory to use them. If you go to like a shooting range, you're gonna you got if you're gonna go there, you got to have headphones on. Sometimes it's good to put something in your ear too. They have little pieces that you can put into your ear. That's what you use that for, because it's extra. I mean, it's that sharp, loud sound. It's so distinctive, or a concert in a large amplifier. I told you before, Trans-Siberian Orchestra. Oh my God. Right in front of the amplifiers, right in front of the pyrotechnics. Could have killed my eldest. I got you great seats. Yeah. If I ever wanted to lose my hearing. And middle ear, nothing big deal about that. Internal ear, this is where we're looking at. All the different structures. The labyrinth is where all of this is located. And so you have an opening or vestibule and the semicircular canals and the cochlea. Okay, and a series of sacs. There are two, if you recall, there are two kinds of thicker fluids called lymph. And this is distinctive from the lymph in the circulatory system, but it has the same name because there's a certain proteinaceous component, gives it a certain amount of, gel might be the wrong word, but both solution and gel aspects of it are the endolymph and the perilymph. So that's significant. And potassium is pretty much the watchword as the triggering agent here. So you can see the way the structure are. Again, the auditory nerve, as we used to call it, is really a combination now of the vestibular or semicircular canal portion and the cochlear going to the hearing apparatus. Not worried about the anatomy or the orientations of the canals. The entranceway to each of the canals, okay, that's the one you might recall the illustration at the end, has a very this crista ampularis, this structure that moves when your head is rotating rapidly. They always show you the illustration of the figure skater and some people are just, like I said, like my daughter could do that. I'd be thrown up on the floor. And she could do that. She knew I loved the spins. I was big into that. And just in case you're worried, her plane leaves probably left already from Fort Lauderdale back here. Don't worry about her.
Good for her. She's having a good life.
You're telling me. That's because she's engaged to a graduate of RMU. Okay, moving on. So let's look at, and the hearing part, we're going to look now more closely at these three areas. The scala vestibule, the scala, so in by the scala vestibule, out by the tympani, and really it's their effects that eventually trigger the scala media. That's the portion where the movement occurs and is able to move that nest, if you recall, inner and outer hair cells. That's what we're looking at. So here you're looking at it a little bit more. And now we blow it up. So perilymph going away from the entry at the round window and then coming about and exiting, in by the oval, in by the oval window, out by the round window. And it's that plays a pivotal role in moving this. And this is the basilar membrane. You'll remember, and we'll see it shortly, and the basilar membrane is sort of the foundation for that media, which contains the thicker endolymph. And that thicker endolymph, the hair cells that are based on the media, on the basilar membrane, are embedded, both inner ones and outer ones, in this tectorial membrane. And it's their motion as those hair cells are embedded as the motion occurs and the inner and outer hair cells move in different directions. effectively, that's the mechanical trigger to allow potassium to enter those hair cells and effectively be the translation of mechanical energy into basically triggering that cell, then obviously connecting to a bipolar cell, and depending on its location and the frequency that was triggered, and then how frequently those triggers come, we're able to analyze and react to, listen to the sound, whatever. So we can look, and that's more anatomy with everything else, but we want to get into what it does. So within those hair cells, the inner hair cells and the outer hair cells, and they're sandwiched again between those two membranes you're going to see shortly here, the basilar membrane and the tectorial membrane. So as you go back, the cochlear branch nerve of the cochlear portion of the vestibulocochlear nerve runs through that, what's called the spiral organ of Corti. So here you can see the fibers, and they're spaced out as per the frequency of the sound that we're hearing. And you have inner and then outer hair cells. And then all of these become, and these are all afferent fibers, basically. So it's a sensory signal. The only motor portion, again, is that little bit that's causing adaptations. And most of that is in the two muscles to the tympani and the stapedius in that area. So just taking a look at it micrographically. And so we can see those things. So the semicircular canal summarizing equilibrium, angular rotation, forward and back, that type of thing. That's in the vestibule of the opening, head position and linear acceleration, and then finally hearing in the cochlea. They've summarized it. So sound, obviously not as fast as light. It takes longer to hear speed of sound versus the speed of light, if you want to think of it that way. So, and again, alternating, without going to the mechanics of sound or sound waves, which I don't know at all. Here you go. So it's based on the wavelength, the difference in the peaks that are there, whether it's higher frequency or lower. So the frequency is just how often it occurs. Your all radiates outward, etc. Not going into any of the pitch, quality. If you have any questions, I have a Liverpool born and fan teaching physics across the hall, or he was. So first thing we look at, it's not the amplitude per se, okay? However, that does play a role, but again, the frequency will cause those crests higher. And this is the old number that we're looking at. The painful area would be 120 decibels, and then over 90 decibel for prolonged period of time is what leads to progressive damage to the hearing apparatus. There. So again, tympanic membrane, auditory ossicles. In the stapes rock back and forth oval window, wave motions in the perilymph. So it's the fluid that's moving. Ends at the round window, and it bulges outward into the middle ear cavity. To some extent, and the sound dissipates. So the helicotrema, frequencies below threshold pass through it to the round window. So it's not necessarily, it may be noticeable to some. The basilar membrane path, things that you and I hear, sounds of my voice, go through the cochlear duct, vibrating the basilar membrane at specific locations based on its frequency. And they'll show you graphically what that means as they sort of stretch out this sort of curved on itself structure, going in, all the way to the tip, going out. And as you can see, different areas of the basilar membrane, to some extent, give us what they call resonance. So it's a certain different, maybe a companion way of sounds that are there. So we begin to see this when they're near the oval window, higher frequency. The farther away, lower frequency. And so there's a certain amount of processing even before the signal gets the receptors. Higher frequency sooner, lower frequency later. And they're just showing how to uncoil it to give you an idea that you can see with it. What actually happens? The basilar membrane, and it's the inner hair cells that are really triggering it more than it. So the cochlear hair cells have microvilli, and we call them stereocilia, even though they're microvilli, okay, that bend at their base. Okay. And so the longer hair cells are connected to shorter hair cells. They call them tip links. And when that force or vibration, that movement occurs, ion channels that project into the potassium-rich endolymph, and that's what causes the auditory phenomena. So bending stereocilia, tallest ones, pulling on the tip links, okay, these are the inner hair cells, potassium and calcium ions and channels in shorter stereocilia to open, okay, flow into the cell. Glutamate, again, here is the neurotransmitter, and obviously, if it's sufficient, we'll get an action potential. Bending the stereocilia toward shorter ones causes the tip links to relax. So depending on how the stereo, if it bends toward the taller or it bends away or toward the shorter, it will hyperpolarize. So, and you'll see in the next illustration the idea of the bend. Is it going towards? Is it going away? That kind of thing. So there's a certain amount of pivoting that goes on, let's say, as the sound begins to dissipate, might be the way to describe it. The outer hair cells of the outer row are efferent. So basically, that's your brain telling your ear. That the other portion, in addition to what it does to the muscles in the middle ear, okay, they can alter the stiffness of the membrane, fine tuning, okay, protecting from loud noise. How many times have you heard something that you wanted to? You heard somebody say, "Let me just listen. I sounded interesting." It's almost like you're cocking your head. But the reality is, I think, is that your brain is sending this message. Listen closely to that, and see if that. To me, that sort of. I mean, obviously, mechanically, it's easier. It's a whole lot easier if you turn the volume up, whether it's on your phone or computer or whatever. Or it's neat if you wanted to eavesdrop in on somebody else's net, which no one here would ever do. Never.
No, it's wrong.
Yes. And off it goes. I'm not, again, loudness, increased number of action potentials, okay, frequency, and that will cause larger deflection. Different positions will be pitch. Localization is how fast. I don't have the tuning fork, but a lot of times it's you hear something from one side or the other, okay, and more of it is about the timing than anything else. Something will go to one side or the other. I know this is another world. When I first started buying records, they were mono, not stereo. We didn't have that. You didn't hear slightly different. You might have heard the same sound, or certainly nothing about like headphone or AirPod technology that we have today. It's light years different. But in those days, we had different ways of listening to sound. So even if you had a pair of speakers that was a mono, you got the same thing coming in both. A couple of bands did start to change that as it began to get more technologically adept. And so balance, different. Balance. So now we're getting into the semicircular canal, the macular area, head in space. So linear acceleration. And I just want to show it to you. I don't spend a whole lot about this. They do have hair cells. And what you see is that the hair cells, okay, in what's called an otolymph membrane. So these are very tiny microscopic calcium carbonate stones in a membrane. Okay. And so and they make it more difficult to move. And so you might remember looking at it, but we're going to look at it again. And they all respond in different planes because I don't have a great understanding of it. It's the vestibular nerve, the vestibular portion. So this is what it kind of looks like. These are the hair cells in the vestibular nerve and the supporting cells in their version of a stereocilia. Not quite the same at all as auditory function. Here you have the membrane, here you have the otoliths. So it's you have to be pretty vigorous or very rapid movement, you would think, to change things. So although they release neurotransmitter, whether it's accelerating or decelerating, will alter and at times create action potential frequencies that are there. So because of the density, it lags a little bit. Okay. So it's a little bit different with regard to that. So bending them may depolarize them, again, increasing the amount of release, and that will indicate positional change. Okay. And bending the hairs away from what they call the kinocilia be less, and it reduces the rate of generation. So you're able to change, and they show you the illustration. So here you have upright. If you're going forward, or if you're going backward, you're going to see changes that will govern the signal that you basically inform. Well, it is really, to me, is informing your brain as to the body position of the head, which may seem like nothing, but plays a lot in folks who are prone, like I am, for instance, to motion sickness. And that was the rotational one. You remember that little thing with that, because we looked at it a bit before. Here, there, the next visual is the micrograph, and the movement of that directionally, as you can see, will you're using so the impact is a little bit different. And again, folks have a lot of problems with that. So the hair cells there, okay, one ear while hyperpolarization the other ear. And so a lot of times it may not be a massive change, but in some individuals it is. It's just their ability to tolerate, or the ability for the signal to say, you're moving fast. It's almost like it's not catching up with your brain. And then it's almost like you're feeling spatially disoriented, positionally disoriented. It's like, and I told you, that's why I'm much better as a driver. I don't mind being a passenger, but I can't do anything. I can listen to somebody or look ahead, but I can't read. I can't go to sleep, any of that stuff. And then we see varied nystagmus is interesting because it's strange. The eye movements and vertigo is something that we do see in the motion sickness. Different kinds of deafness can be mechanically oriented, whether it's earwax or damage to an eardrum or infection or anything, or the bones are starting to sclerose, or it can be more nerve oriented. And neither one are terribly easy to deal with. The default is always amplification, as we do when we eventually at the end of the term do the aging unit. It just comes with the territory. It just does. Rather than, as my wife informs me, for men, we have selective hearing. We only hear what we want to hear. You have never noticed that. Bad. I'll reinforce this. Overusage of aspirin is notorious. And if you know somebody who has tinnitus or tinnitus, as I say it, but I think it's pronounced tinnitus, it is, to constantly have a sound in your ear is awful. If you ever talk to anybody with this, it is terrible. And this is worse. Meniere's an autoimmune related problem. It is absolutely intolerable, etc. By that, more or less, getting near done. Curtail your excitement. Trying to think if there's anything functionally apropos in this one. Yeah. It's all right. I didn't know she was leaving. Yeah, this nugget here. Again, you remember me talking about it, but it doesn't hurt to reinforce. This is the idea of regenerative axons. We don't, the closer it is to the cell body, the less likely it is to occur. But it's why we can replant limbs or replant digits, and many times. Really, the limiting factor is how fast and decomposition. If you happen to see somebody who has something chopped off and you can grab it, a finger, a toe, what you should do is, if you can, clean water, pinch of salt, plastic bag, put the plastic so you have somewhat of a saline solution, and put that in some ice water in another bag. Ice directly contacting it is more problematic. You want to keep a isotonic environment, and typically a little pinch of salt and water will be close enough for government work. And then you can put that in, and you get that and them to the hospital as fast as possible. That's the first thing. If it's clean, we had a case. Did I tell you about this? The butter case. Huh? Did I tell you about the case with the finger in the butter?
No.
Oh, good. There was I forget which dairy, maybe Breakstone's butter in Philadelphia, about 3 or 4 small city blocks from our hospital, and this kid was working there. They're making like the sticks, that we typically get our butter in, like here, and what it was in the butter. So they brought the butter with the finger in it. And we tried. The trouble was the oiliness and the fattiness was the circulation really impaired it. So they brought it to us in the butter rather than getting as much of that off, gently cleaning it. Well, not that they would know. It's not a fault. And it wasn't a tremendous amount of functional impairment, to tell you the truth. The other thing that when we tried to replant it surgically, the orthopod wasn't there. The general surgeon was. And if you wanted to just use it, he said it would, because it was mostly distal phalanx, we should have removed the bone, because that would have been the part that would have been compromised by the butter, more so than the soft tissue. So it necrosed. We sewed it back on, and necrosed means it died, turned black, and it fell off. So what it does is what we call a biological dressing. So when you're putting a piece of you on top of an open cut of you, it's okay. It's like why we leave the roof of a blister on. This is a biological dressing. So it was interesting. Yeah. But imagine here it comes in. His buddy comes in with a block of butter. It's like, me. You can have it. Goes, you can keep it.
He kept the butter?
Of course.
Did he eat it?
It's butter.
You can't waste the butter.
You can't waste butter. Not where I come from. See, for those going into medical fields or working in hospitals, these are just the little things you see every day. There's nothing unusual that any person who is a resident in a big city hospital wouldn't have seen, because you see it all. You have no idea. It's so much fun. So this is why replantation works. What we found out over the years, you don't have to sew the nerves together. Anything distal to the injury will degenerate down the axons, but macrophages, will come in and clean it up because they're summoned to the area by tissue damage. The Schwann cells get stimulated by that same group of chemicals or pro-inflammatory chemicals, and axon filaments will grow through something that develops called a regeneration tube. We found out you didn't even have to, even putting a little needle, even with a very, very fine, like a 5/0 or 6/0 suture, which is, and the more O's, the finer it is. Typically in the skin, you use 3/0 or 4/0. Okay, so you get 6/0, 7/0, you're getting, it looks like a hair. And that would actually cause damage, more damage in the sheath than it worked. And they developed materials that were biocompatible that you could just put the cut ends of the nerve in and they would seek each other out. When we amputated, we made sure that nerve seeks out other nerve. You have to bury it in muscle or bone to stop it from growing. It took away a lot of phantom limb pains and stump pains that were associated with those kinds of things. It's a science unto itself. And you learn about all these things because the people you work with have so much experience that they share it to you. And most doctors, that's where they'll tell you stuff that their mentors or their attendings have told you. Many of the stuff I come from. So they grow through this tube and then the new sheets will form. And it looks like this. So at the site of the damage, you can see it's disrupted. You can see the nerve is disrupted. That's there. But you still have myelin, you still have Schwann cells that are in the area. And then what will happen is it begins to regenerate. So the macrophages remove the debris. There's going to be surviving elements. They're going to secrete additional things that are going to accrue chemicals to it. So, and that's standard. And now we begin to see this as it comes together. The Schwann cells form what they call a regeneration tube. And we saw it clinically. People who said, I can't feel this where you did the surgery. And a year later, it worked. I can feel everything. What a country. Boy, you did a great job. Hey, I can take yes for an answer.
Okay.
And voila, it's regenerated. And they grow, we're talking, it's like slower than hair growth, fractions of a millimeter over a week. So it's tiny, tiny increments that they grow. The other thing that was important with limb replantation is venous drainage. I may have mentioned it before. Getting the blood there is important. The trouble is blood has to come back. There's always at least 2 or 3 veins for every artery. So you increase the amount of veins that come together. You learn that because we had a plastic surgeon who was very knowledgeable of that because he did a lot of tissue and related grafts. And these were in the early, before some of the major changes. They were doing a gender transition on a guy to a girl in the early days. And this guy was doing a lot of plastic. We were doing it in our hospital, which was very, I wouldn't call it risky, but unfamiliar territory might be the way to describe it. Okay, so we're talking, before 1980s, 45 years ago. Did the cranial nerve nugget. If there's anything on here, I'll let you know. Test-wise. Spinal nerve nugget, we did. Plexes, we did. This is all anatomy. God, I remember, it's like it was yesterday. Okay. Tell me about sciatica. Love that with the dermatome. I don't think there's anything really left in the chapter. They're important, but that's basically how we do testing. Physicians, you can always find the thing anywhere, but you want to look for those types so you know what nerves you're testing when you're doing testing. Okay. All right, we're going to do the EMG and nerve conduction lab and call it a day because I have to go to Sam's Club. I have to bring by myself, unless I get help from one of you. No, a 50-pound bag of wild bird seed.
Why do you need so much bird seed?
You have no idea how many animals. My mother-in-law, for the last 60 years or more, feeds every animal. They all flock bird feeders, deer feeders, duck feeders. They're animal crazy.
Can you get smaller bags of all?
Yeah, not cheap. I don't want to go to Walmart and get the little box. We feed that to the cockatiels. This is the 50-pound bag of, oh my God. And it goes like in 2 weeks. Oh yeah, Bird City. I mean, you would think there's an Alfred Hitchcock movie coming our way. Yeah, watch that if you want. That is Dakota Johnson's grandmother is the lead in that, Tippi Hedren, whose daughter is Melanie Griffith, whose daughter is Dakota Johnson. In case you're wondering, she was the girl for those movies, for a couple of Alfred Hitchcock movies. Not a very pleasant director to work with, but I digress. All right, so here's what we're looking at. This is the lab for today. So I have up here the following. So this is effectively what we're looking at is the relationship, and we're going to need somebody wrong to volunteer to grip. There we have a volunteer here in New York. So when I say get a grip, you will. So we've plugged the I wire into the IXTA, I think we have here. And now I got to get the red, black roads. We're going to plug the grip sensor, which I have here, into the IXTA. So they're all hooked up, and I have them on the two appropriate places. We will, up here, I'll need someone to assist to put these leads on, because it's hard to do it for yourself, on your forearm, red, black, and green in that order. Green toward the wrist, red up to the elbow, okay, black in between them, in that fashion. We just need one set of leads unless we have someone else who wants to volunteer. Okay, I have to set the offset. So when we're up here, I'll go back to this. We record, well, I can record that now. Click stop, move the two vertical cursors so they're 5 seconds apart, and I'll click and I'll do that. It's easy to do. And then the person, subject, quietly with his or her dominance of your right-handed, on the tabletop. So you can probably sit over here and do it. And we'll squeeze the grip sensor 5 times, 2 seconds each. Rest 2 seconds in between, 2 seconds each. Okay. Use only the fingertips, not the whole fist. So, and then get used to that. But then what you're going to do is light, stronger, continue by squeeze 5. You should be putting everything into it. Okay. That's the practice. Click record, and we'll scale in the midst of all of this to get it and get a file created. So what we're going to see is we're going to see activity here. You notice how it increases. And we're going to see here activity here. So we're going to see electrical and physical activity is what they should reflect. And as you can see, we can analyze it by put the whole recording on one screen, sort of bring everything together, and voila. So you have all of this available to you, and then there's all the things that are there. Now, the second experiment, you don't have to take anything off. You can just do it, okay, is fatigue. And this is harder still. So you're going to squeeze the bulb, fingertips only, as hard as you can for as long as you can. So it should be between 1 minute and 2 minutes. And I'll auto scale while we're doing this. And finally stop when you released it. And we'll take a look at what happens mechanically here and electrically here. So hopefully we should see these correspond. Okay. Effectively, we're working that. Let me go back to the auto scale part of the program. And okay. Well, someone has to help. Who wants to help me set this up? You're coming up here. I see. We have a volunteer. Okay. Put this back here. So you get to do that. You want to screw the red. I've already got the black in with the black, the red in with the red, and you can see them over here. So you can come over here and do it. After you're done with that, when he comes up, we're going to put these on. So these, and hopefully on the least hirsuitous area you have, less hairy. And you just have to pop that on here, here, and here. And so again, red, black, green, I think is how it is. Yeah, red, black, green. And the green is the ground. We have plenty of those. So I will do the offset.
Do you want me to come around?
Yeah, give me a second.
All of them?
Hmm. No, just those three. We only use three. Hold on, I just want to set this. I always have to check. Vertical cursors 5 seconds apart. Hold on. V2, V1.
Okay, yeah, for experimentation. Okay. Can I put these on now?
Sure. Middle one.
I know it doesn't go there, but I was like,
Okay. That's,
yeah, I know. I just.
so you need to grab yourself a seat when you do this too. And then this is your squeezer. Okay, that was good. So you can sit there. I'll do it here. See, we can move this stuff out of the way. Getting your leads on there and not doing a whole lot of hair to contend with. Which is good. Thank you. Now you want to put them on. Yeah. Close enough. Okay. Red, black, green. And they just snap on. I just got. Those are expensive. I'm not these. I found ones that were generics. I mean, they wanted like for
Black,
like you know, like
green.
like for a hospital, they're like $1 a piece. You know, for you can get them for 10 cents a piece. It's ridiculous. I mean, these these little those things, the little sticky things with the nub on it. I mean, it's ridiculous. So you want to get yourself closer to the table because this is when you're. And I'll read to you the instructions again. Okay. So what you want to do is dominant forearm resting on the tabletop, and now fingertips, not fist, fingertips. Yeah, back more fingertip, less palm, thumb and fingers. No. Tips.
Don't let it touch your palm.
Don't let it.
Okay.
We have liftoff. So what you want to do is just squeeze it a little. Over 5 squeezes go from a little compression to really squeezing it hard and holding it for 2 seconds with a 2-second break. That's what we're trying to duplicate. Okay. Tell me when you're ready and I'll run a test pattern.
All right, I'm ready.
Okay, hold on. I will tell you when to start. Take a break. Okay. Go. Well, that didn't help. Okay, stop. I mean, I auto scaled it too fast. Okay, hold on. I'm going to discard that. We're going to start again. The hard part about that is stop it. Okay, just take a break so I get organized. So the offset theoretically should have worked there. All right. Begin. Oh, I hate this. Stop. I screw up. Give it a stop, would you? Okay. And I'm going to discard. I'm going to X out of this in a second. Let's do it this way. I'm going to start again. I'm going to start again. See if I can get this to work better. Okay, you ready again? I'll tell you when to start. Go ahead.
All right.
You done? Okay. You right?
Yeah.
Let's see if we can get these closer together. Okay. Let's see how this works. Not as good as I thought. I can't use the auto scale. Okay. What we're going to do, okay, let's try it a little bit more. We'll make it a little more. Put it down for a second on the thing. I'm going to re-offset it for a second. All right. Yeah, just let it sit there. I am going to let it run. The hard part is what I'm trying to do, everybody, is to get it so you guys can see it. Okay. All right. You going to get ready again? Let's see if we can get this to work a little bit better. All right. Whenever you're ready. You're done? You're still going? He's done. Okay. Let's see if just use it. I'm hoping we can get this part so it should be close enough that we'd be able to see it. But we're trying to look at, as I bring these a little closer together, is so we can see 1, 2, 3, 4, 5. I'm trying to get this adjusted, but we can begin to see the amount of force or pressure, and it should be increasing. So the bottom here should be increasing a little bit. I wish it was a little more accurate, but this isn't too bad. Okay, so yeah, grip strength versus the force, the electrical activity combined with your muscular activity. So let me do this. Ta-da. Okay. The next one is a fatigue activity. So you're not going to like this as much. So everybody, we're almost done. Stay with me. And same deal. We're using the same parameters that are here. The distinction is its amount of how long am I going to have to contract it. So in procedure, so you can see what we're looking at. I was hoping to see this, and I don't know why my adjustment isn't there. And I'm hoping I can find a way to adapt that bottom icon to look at this a little bit better. But if not, we're okay. Now this one's a little bit different. Okay. Okay. Now, here we go. So this is strength and contract. So we want to see how the pressure and what happens with the EMG activity. So once I start, I'm going to tell you to start. Once I start recording, you're going to squeeze that just like you're holding before as hard as you can. And we have to go for between a minute and 2 minutes. Okay.
Okay.
So, and we won't stop until you release it. And then I have to watch it sort of until you've released the bulb and your strength has dropped by 50%. So we'll go for, let's say, a minute and then release it or whatever. You can tell me. It's not going to be necessarily easy.
Release it at 50%.
Pardon me. Yeah, no, we're going to, between it, once it's released, we'll stop this. So we want to see how it goes down, if that makes any sense. How the degree, the length of time it comes to respond. And all right, so tell me when you're ready to start. I'm going to start recording. So are you ready to start within the next few seconds?
Yeah, like this, right?
Yeah, exactly. Same way, but as hard as you can. And then I have a timer obviously going here that I can see. Nope. It's too soon. Don't look at me. You discard that, bad boy. I want it to run a little bit. Okay. Oh, no, let's cancel. Let's save it. Okay, let it run, and I'll tell you to start. Go. Hard as you can. Don't quiver. It's a quiver. Hold it. I know you can do it. We need a little encouragement. Oh, go. You can do it. We have a winner. We're almost there. You have 30 seconds into this already. 20 more seconds. Can you do it?
Yes.
Oh, my dog.
At least 10. Can you go more than 10 more seconds? You can do it. He works out. Keep going. Almost there. Can you hold it? Now you're past that minute. How long do you want to hold it? Tell me when.
Keep thinking about your dog.
We only have 3 more minutes.
Terrible. All right. I want you, okay, get ready to release it. And we'll go to minute 30. We're going to do a minute and a half if you can hold it. All right. You're going to release it in now. Now,
It was totally working.
poor hand.
You might have purple tongue now, but it's okay.
Wait, keep that hand. You're making, no. You're not supposed, no one told you to do that.
Okay.
Ignore that little blip that came afterwards. All right. When you, I know you did. I know you're doing it. So what we want to do is we bring this closer together. You can see that little blip is just his moving, which we don't necessarily have to have in it. Thanks. Now here we are. This is roughly, I think this is about as close as you can get it. So you can take a look here. I don't know why this is creating such a problem with the force. And I'll see and if not, we can always redo it. But let me save this.
Do it.
No, not today. But you can start taking off your leads and everything. Okay.
You do like the mini crossword and I don't even do this. I do. I just don't.
Success. All right. We have completed this. All right, everybody. So that's everything for today. Thank you very much. I will distribute that and have you look at it, make a couple of observations about it. Pardon me? Oh, I mean, that's for you to do, not for me to do. I've done this already. Goodbye, everybody.
What are we doing with the results?
I will put in a I will give you a